Let's now continue on by adjusting the right combination between velocity, temperature, and pressure. So right now, most of our temperature and pressure is coming from the combustion itself. So if we go to our pyrosolver, go to flames, it's all of this that's being generated. That's mostly pulling things up in the air. And one reason why our temperature was getting so crazy is because in our source, if we go down to flame, we're adding at each time step, which means that with each time step that combustion source is there, we're adding 1 unit in flame. That in turn is bringing up those flame values to close to around 9 or maybe even 10 units. And the more units of flame you have, the more you generate this temperature and expansion. So whenever you're working with flame, I'd recommend setting this to maximum so it doesn't add on top of the last time step. That way the flame always stays around a value of 1, roughly speaking, and that will allow you to better control temperature and expansion when that goes to contribute towards your simulation. So we're going to do that. Also, I'm going to take up this flame lifespan because we're not adding in that much flame anymore. So I'll take this up to 3 seconds for the flame to dissipate completely. And that already will make a huge difference because imagine this temperature amount getting up to, well, like I said, maybe a value of 7 or 6, but now it's going to a value of 1. That's a big difference. Likewise for this expansion. So we'll have to see what that does. But I also already know ahead of time that the velocity is something that I want to really rely on for that initial motion. And based on the values that we were getting last time with the axiom solver, I know that this is something that will have to turn up a fair bit. With the velocity, I'll add that in and set the scale here to 10 to get us started. Now that's already a lot of changes, so let's see what that does after we cache this out. And it looks like the velocity really poofed out that main mushroom cloud shape quite a bit, which is nice. I think it's going to work really well, especially when we try to have the spikes go through there. In a lot of reference, you see this kind of big plume happen, and then that becomes the backdrop for the spikes to go through and pull things out from there. However, the temperature is still too hot, or maybe better said, the buoyancy is too strong. The temperature values are all right as they are, perhaps, but if we work on the buoyancy now, we can probably get a better result out of this. And one thing that I want to also point out is that you never really see in Houdini simulations these clouds on the outside falling down with gravity. And a lot of times too, you don't get enough rolling out of these clouds. So to give you a good example, let's go back to our reference and I'll show you what this rolling motion really looks like. I want you to pay attention to the smoke plumes and how they evolve over time. Notice how they're basically going to be going in circles. It's almost like there's density coming from within the plume and going inside of the plume at the same time. So watch. Especially like over there. You just have so many little sections that are rolling around. And because of that fact, it makes sense to add a bit of gravity to the outside of the plume so that it goes down, and to add a bit of buoyancy to where there's a lot of temperature. The combination of those things is going to give you that rolling motion a lot more. This is probably another decent example where we have that rolling motion happening, especially right there. You can see it big time over there. And so, like I said, if we work on the buoyancy, we can get those rolling motions while keeping more control over how high and how quickly this whole thing pops up. Going back to our DOP.NET, the way we can do that is through a combination of a couple of things. For one, if we go down to our temperature, we should remap this to the flame. And what that basically means is that if the flame is 0, the temperature is going to be 0. As soon as flame reaches a value of 1, we have this full temperature amount happening. So it makes sure that at the lower values of the flame field, that you're getting let's say 0.2 of the temperature from that. So as flame goes down, so too does the temperature contribution. Likewise here for the expansion or the pressure, same thing. We want to include this ramp, and we can mess around with that a little bit later if we want, but that's going to help a little bit already in controlling that temperature. But like I said, the main driver here is buoyancy, and if we look at the ambient temp and the reference temp, the closer these two guys are, the less buoyancy there's going to be. So the ambient temp in this particular situation is 300. I want to make this about 1,000. And that's going to decrease the buoyancy of the simulation. Now, the one reason why I like decreasing the buoyancy is because I also like turning down the cooling rates. I like having the temperature cause things to evolve more and more over time, and I don't like that effect to go away so quickly. So that's why I turn down the cooling rate usually, but that also means that I need to turn down the buoyancy because with the temperature lasting longer, it means that it has more time to affect this buoyancy right here. So that's one reason why I do 1,000 and 3,000 for that. Now, we do have this gravity over here, and that's all right, but it's not going to give us that swirling motion that I mentioned. The reason why this gravity won't do that for you is because it affects everything equally. And I need an area that's next to a hot temperature zone to go down to create those swirls. So in other words, I basically need a situation like this, where we have temperature, this red area going up, and we have the velocity going down in these blue areas. That's what gives us the swirls. So to do this, we can utilize a gas buoyancy. And this gas buoyancy has a setting that's very, very underrated and amazing. It's this ambient temperature right here. And so what this will do is any temperature value that's less than this is going to go down, and any value above this is going to cause things to go up. So to see what this does, let's take our buoyancy lift here to 9. That's about on par with what gravity is. And for our pyrosolver here, let's set the ambient and reference temp to be the same thing so that this buoyancy isn't doing anything, and the only buoyancy we see is coming from this microsolver. When we do that, what happens? When that happens, we end up with this blob. And it's not ideal because we're not getting that swirling motion. Again, why is that? Well, because there's nothing going down. I haven't actually set the reference temperature or the ambient temperature here to anything beyond 0. And so when determining what to set this to, we need to figure out a nice temperature value that correlates with our simulation. So let's go down here to this volume slice. I set it to temperature. The red areas, again, are going to be values of 1 for temperature. As I turn this up, we can see that our temperature goes up to around a value of 6. And what I like doing for this particular setting is I like keeping most areas going upwards. But these blue areas, the green, yellow, etc., I do like leaving a little bit of that to get that downward motion as well. So let's take this at maybe a value of 0.9, maybe 0.8. That seems to be pretty dialed in, visually speaking, to what will make this swirl around. So back here to gas buoyancy. 0.8 is going to be the ambient temperature. Now what happens when we re-kick this? Okay, and now we have this awkward simulation. But I do want to point out that things are at least falling down now. And that's a really, really good thing. Obviously, this whole thing is super blobby, and I'll tell you how to fix that later. But just looking at the overall motion, we're getting that success in bringing things down now, which is great. It's not a huge impact, though. I'd like to maybe see a bit more buoyancy out of this. So if we go out to the dot nets, or perhaps even a little bit more things going down. So we'll turn this ambient temperature to 1, this buoyancy lift to maybe a value of like 12 or 15. I don't know, split the difference and go 13.5. And I think that'll help things out quite a bit. Now, I don't like keeping this ambient and reference temperature the same. That is going to go back to 1,000 and 3,000. But just one more time with this gas buoyancy, I want to see what this is doing by itself before I bring in this ambient temperature and all that. So one more time, let's check this out. Okay, and now we have this. Obviously that impact is still pretty awkward, but you know, in general, this is heading in the right direction with how much downward motion we have. I would like to take that ambient temperature or that threshold down to about 0.7 again. I think there's too many things going downwards now. I want more temperature areas going up, but I do like the overall speed of things. So we're going to roll with that. And also what we're going to do is bring back the values over here. So let's say 1500 actually, because I'm going kind of aggressive on this gas buoyancy. And the ambient temperature, let's say, is going to be 0.7. Once we have that, what does that do? Okay, and now we end up with this, which is looking pretty cool. Now, again, we still have that awkward sort of start to the explosion where it just hits the brakes really fast. But what we might be able to do now is add a bit more velocity for that beginning part right around here. Because right now our velocity is going about that far, and we can probably push that a bit further, honestly. But the main thing with the temperature is, again, to focus on that evolution, that progression of the smoke plume. And this progression, I think, is looking pretty nice. Remember also that we're going to have spikes coming through this thing. So we do want to have it a little bit floofy like this so that we can add in the spikes later on. In the next video, let's adjust the velocity. Let's also take a look at pressure, and we'll be talking about the CFL condition and substepping a bit more as well.